Okay, hello everyone. In this video, we will introduce probability distributions, the continuous case. So far, we have talked about the discrete case when we have discrete variables. Now, let's check what are the differences when we are working with continuous variable. So there are some differences. So the first one is that if you try to compute the probability of an exact value and if the random variable is continuous, then the probability is going to be equal to 0. So that's a big change right there. That means that the equality doesn't matter. So therefore, if you want to compute this probability that the random variable is less than one value, that's the same thing as that the probability of x that is less equal than the same value. It's exactly the same again because the equality doesn't matter. The equal sign does not affect the operation. Similar, if we have greater, or it's equivalent to greater equal, and of course we have all these expressions here, they are all of them are equivalent. So x between a and b with the equality sign included, so it's the same as if we remove the equality from the lower limit, same thing if we remove it from the upper limit, or if we remove it from both, right? It's the same, so we're getting the same probability regardless the expression that you use here. It doesn't matter. It doesn't matter. So that's the first thing that you need to consider. Alright, now in terms of the probability distribution, which we call, remember that in the discrete case was called the probability mass function. So now here we call it the PDF, or probability density function. It has some basic properties. So first, the PDF has to be greater equal than 0. If we do the integral from minus infinity to infinity of the PDF, it has to be equal to 1. So this is the equivalent. In the discrete case, remember that the sum of all of the probabilities, they have to be equal to 1, so this is the same, right? But in the continuous world, instead of the sum, now we use the integral. That's the main thing that will change. And if we want to get the probability in an interval between a and b, then you have to do the integral between a and b of the PDF function. Alright, so let's practice. So this is how it looks, a general PDF function, and if you do the integral between 2 points, you get this area. Remember that one of the properties is that if we do the integration over the whole area, so that result has to be equal to 1. Okay, so let's check this example. So we're given what it looks like a PDF function. We need to check that. So it's x squared over 3, and x is defined between minus 1 and 2, and of course it's 0 otherwise. So the first question is to verify if it's a PDF, a probability density function. So we need to check that first. Is this expression always greater or equal than 0 in the interval where x is defined? So for values that are below minus 1 and above 2, so the PDF is 0, right? So it satisfies the condition. Now between minus 1 and 2, so if you plug in any value between that range, you will find that it is in this case it's always positive or equal to 0, right? So it satisfies the first condition. It satisfies the first condition. Now let's check the second one, where the integral from minus infinity to infinity has to be equal to 1. So we do the integral from minus infinity to infinity of the PDF function. So remember that it is defined from between minus 1 and 2, and for other intervals is equal to 0. Therefore this expression is equivalent to the integral from minus 1 to 2 of x2 over 3, right? Now if we do the integral, then this will be x to the power of 3 over 9 from minus 1 to 2, right? Those are the limits. Then if you evaluate the function, so this is a 9 minus minus plus 1 9, so that's exactly equal to 1. So it is a probability density function. It is a probability density function. Now if you want to do the integral, if you want to find probability between 0 and 1, then you need integral between 0 and 1 of the PDF, right? You already know the result. So it's the only thing that changes here are the limits, because are between 0 and 1. So in this case it's 1/9. That will be the probability between that x is going to be between 0 and 1. So here you have the results in a cleaner format. Okay, let's check a second example so we can practice a little bit more and get used to how to work with PDFs and the integration part. So let x be a random variable that measures the diameter of a part. The ideal diameter is 12.5, that's the reference. However, previous data show that there are parts with a higher diameter. So the PDF is as follows. So 20 times e to the power of minus 20 times x minus 12.5. So this is important. X is defined for values greater or equal than 12.5. So for values below 12.5, the PDF is equal to 0, right? That's the meaning of this expression. So the question in here is to find the proportion of parts with a diameter greater than 12.6. So initially, we want to find what's the probability that x is greater or greater or equal is the same, doesn't matter. What matters here is the greater part, 12.6. So this is equivalent to the integral from 12.6 up to infinity of the PDF function, right? X minus 12.5. Now, since this variable is defined for values of x greater than 12.5, so we can rewrite this expression, and we can change the limits. So instead of trying to do the integration from 12.6 up to infinity, we can do 1 minus the probability that's between 12.5 and 12.6, and it's going to give us the whole area. So let me show it to you in this plot. So this is the PDF plotted. We know that the whole area, including the white space here below the curve, the whole thing is equal to 1, right? From 12.5 up to infinity. But the area that we want to compute goes from 12.6 up to infinity, right? So what we're going to do is let's take the whole thing. So 1, that will be the area, the whole thing. And let's remove only this part. Let's remove that section. If we do that, we will get the desired area, right? So that means that the desired probability is equivalent to 1 minus the integration from 12.5 up to 12.6, right? So we're removing this white space here, and we use, of course, the PDF function. And that's it. Okay, so you need to practice the integration part, because it's not in the reach of this course. That's a prerequisite. So it is up to you to practice all like how to do all the calculations. So just to give you an idea, if you use substitution, you can solve it easily. The integral that was defined here, right, is the same that we have here, right? So at the end, once you do all the work, you will get that the probability that the diameter or the random variable are going to be greater than 12.6, that probability is equal to 0.1353. 0.1353. Okay, so remember that we have two functions, right? The PDF, the probability density function, and in addition, we can get the cumulative distribution function, as in the discrete case. So in the discrete case, to get the CDF, we use the sum of the random variable up to a specific value, right? So this expression is the same, probability that x is less equal than specific value, right? But here, instead of the sum, we will have the integral from minus infinity up to x. Here we change the variable. This is just an alias to avoid confusion with the limit, right? But don't worry about it. We're using just t as an alias to avoid the x here in the function and the x in the limits. The nice thing about finding the CDF is that we can use it then to find probabilities without the need to do the integration part. So if you want to find the probability that x is between a and b, that will be only the difference between the CDF of b minus the CDF of a. So that difference is going to give us the desired area or the desired probability. I think at this point it is obvious that if we differentiate the CDF, we get the PDF, right? Or if we do the integral of the PDF, we will get the CDF. Alright, let's check a quick example of the CDF function. So we are told, this is the same example that we solved at the beginning of the video. So we're given a function, which we already know it's a PDF, right? And we want to find the CDF, right? Please check the notation. The CDF is always referred by using capital F, while the PDF is with the lowercase f. Alright, so if we want to find the CDF in this case, the fx, so that will be fx, it's equal to the integral. In general, it's from minus infinity up to x, but here please notice that the lower limit for the PDF here is minus 1. For values below minus 1, the PDF is equal to 0, so there is no point to do the integral between minus infinity and minus 1 because it's 0, right? So here instead of minus 1 and instead of minus infinity, I will begin the integral from minus 1 because that's the lowest point where the random variable is defined up to x. We want to leave it as a function of x. That's why I'm using x in the upper limit. Then I use an alias for the variable. So let's use the PDF. It's x2. But I'm going to use t2 over 3 dt. It's just an alias again to avoid confusion between the variable and the limit. So we do the integral, and this is t3 over 9 from minus 1 to x. So finally we will get that this is x3 plus 1 over 9. And that's the CDF function, which usually it's written in a different format. It's more like in a interval format. So we can claim that if x is less equal than minus 1, then the cumulative is 0, right? It's not defined. But we know that if x is between minus 1 and 2, then of course we can use the function that we just found because we do the integral of that expression. So that will be x3 plus 1 over 9, right? And if we're getting values of x greater than 2, since this is cumulative, so if x is greater than or equal to, since this is cumulative, then of course the area or the cumulative probability is going to be equal to 1. Remember, this is a non-decreasing function. This is a non-decreasing function, right? So here we have all the work. So remember, this is the CDF, and this is how you write it. This is how you write it. You need to define all the range, all the intervals from minus infinity up to infinity. And actually there are some problems where the PDF is defined in different intervals. In this example, it only was defined in one interval, but later on during the class sessions we will practice those cases where the PDF is defined in 2, 3 or more intervals. So you gotta be careful when you're doing all the calculations. Alright, so now let's do part B. In B, the question is find the probability that x between 0 and 1. So maybe you're tempted to do integral from 0 to 1 of the PDF. That will give you the answer, but it's better and faster to use the CDF. So if you already have found the equation, then there is no point to do all that estimation by hand. So let's do the probability that x is between 0 and 1. Remember here that equality doesn't matter. The equality here doesn't matter. So this is equal to the lower limit, the CDF of the lower limit. So this is the cumulative probability up to 1 minus the cumulative probability up to 0. If we do the difference, then we get the area between 1 and 0, right? So how do we get F1? So we just go to the CDF function. We check, okay, this x where it's located. It's located in this interval, right? For that interval, then the CDF is given by this expression. Same thing when x is equal to 0. It's the same interval, right? So we just plug in those x values and we will get the desired CDF. So when x is equal to 1, the CDF is 1 over 3 plus 1, that's 2. That's 2 nines. 2 nines. Then we find the CDF when x is equal to 0. We plug it in, it's 1 9. Then the desired probability is 1 9. Right? So this is how the CDF looks, a non-decreasing function that we will be using in the upcoming problems. Okay, remember that we talk about expected value. So it's a theoretical value that shows you what will be the average of the random variable after many observations. So the equation in the discrete case is the sum of the outputs x times the probability, but here instead of probability we have times the PDF, right, the probability density function, and instead of the sum we do the integral from minus infinity up to infinity. In the case of a function, same thing, so instead of the variable we have the function in the integral. So the equations are pretty much the same. Of course the changes are instead of sums we're using the integration part. Lastly, the variance. Actually I think maybe you will remember this equation. The first part, this is like the expected value of x squared. So it's just the integral from minus infinity to infinity of x squared times the PDF. And once you get that, you just deduct the mean value or the expected value s squared. That's how you get the variance, right? So let's check this example. The probability density function of the lifetime in hours of an electronic product is as follows. So we're given the PDF. It says 20,000 over x3, right? And that's defined for an x greater than 100, and it is equal to 0 otherwise, right? So let's do the expected value, e. So using the equation, the expected value of x, remember this is mu, it's equal the general expression from minus infinity to infinity of x times fx dx, right? So random variable times the PDF, the probability density function. So let's do that. Let's do that here. Now, we don't have to go from minus infinity in this case because the variable is bounded. So it's for values that are greater than 100, right? The PDF is 0 for values that are below 100. Then our integral will be from 100 up to positive infinity, right? X times the PDF. So please notice that the x is going to cancel. So instead of x to the power of 3, we will get x squared, right? Because we're multiplying x times the PDF. That's the equation of the expected value. So this is 20,000 over x squared dx, right? So we do integral and we get that this expression is going to be equal to minus 20,000 over x, and that goes from 100 to positive infinity, right? So if we evaluate the function, you will get that the expected value is equal to 200. So that means that the expected lifetime in hours of the electronic product is equal to 200 hours. 200 hours. So what is the meaning of that? That means that if we take the different electronic the same product, like but different units, and we evaluate the lifetime of them, some of them will be above 200. There are some of them that will be even below 200. But when we compute the average, it's gonna be close to 200. This is a theoretical value. That's a theoretical value. It's a reference. It's a reference to know like where is the centrality position of most of the values of the random variable that we are discussing. Okay, guys, this is everything in this section. During the class session, we will go over different problems to practice these concepts.